morning, and I hope you're excited for our first talk of the day. Kang Hao He specializes in real-time system engineering. He joined the 3D graphics team behind Far Cry 6 to deliver great visual experiences for players on console before moving to Ubisoft's Anvil Engine core tech team, where he's currently working on low-level rendering system development as well as making improvements to engine architecture. Andrew Gilner is a 3D graphics programmer who started his full-time game industry career as a junior 3D programmer in 2015 at Ubisoft and left as 3D technical lead in 2021. Before joining Sony Santa Monica Studio, he briefly worked at Electronic Arts on the Frostbite engine, and Jendrik specializes in game engine architecture and GPU-driven rendering techniques. He runs a very popular weekly roundup of graphics programming-related news. Without further ado, please enjoy their talk, Lessons Learned from Establishing a Long-Term Vision for Far Cry, Dunia Engine's Shader Pipeline.
Good morning, good evening, or whatever time it is for you right now. Thanks so much for coming to our presentation about the shader pipeline on the Far Cry Dunia engine. We will be talking about the long-term visions, the lesson we learned, and everything in between. Who are we? My name is Jendrik Gilner. I'm a senior rendering engineer currently at Santa Monica, where I started in 2022. But this talk is not about my time at Santa Monica, rather it's about my time at Ubisoft Montreal, where I joined in 2015 as a junior 3D programmer to work on Far Cry Primal, and have worked for a number of years until I finally left in 2021 as a 3D technical lead on Far Cry 6. With me today is Kong.
Hi, I'm Kong. I'm a 3D programmer currently working at Ubisoft Montreal. I joined the company back in 2019 to work on the latest Far Cry 6 with Jendrik and the rest of the team in Montreal. Previously, I was more into a system engineering side of things for graphic driver, SDK development, and computer vision. Looking to try something new, Far Cry became the first AAA title project on which I worked, and from which I learned a lot. So, without further ado, let's see what we have for you today. Here's an overview of today's presentation. We will first explore the challenges encountered on working with a legacy codebase from Far Cry 3. Then, we will discuss our long-term tech vision for supporting that new API and our shader pipeline system. We will also dive into details on how we executed our plans for architecture change, bringing our visions to life. In the end, we will talk about testing, fine-tuning, and polishing the rendering system of Far Cry 6 and the lesson learned.
But before we go into all of this, let's have a quick look back in time to understand where we are coming from. Far Cry 4 is being released in 2014. What else happened in 2014? D3D12 has been announced. And if we look back at just 2022, 2021, we see that's when Far Cry 6 came out, and that's when D3D12 support was at the very first time. You can see in that time of 7 years, a number of other Far Cry games came out, but none of them used D3D12. Far Cry Primal was released in 2016, Far Cry 5 in 2018, Far Cry New Dawn in 2019. All of these projects have set the architectural foundation that we will be talking about in this presentation. But all of it really only came together for Far Cry 6 in 2021, with our very first game supporting D3D12. So the big question is, why did it take so long? As you might be aware, there's a huge difference between what D3D12 expects you to be able to do and what lots of engines out there can really do. Dunia architecture was designed in a way that you need to know very little ahead of time. But D3D12, on the other hand, needs to know as much as possible ahead of time. So you can see these are really the two opposite ends of the spectrum. And all of these years, it was really making sure that these two extremes can come together to meet in the middle and take advantage of both of them. And to do this right, you have to think about long-term strategies, how to address these, and keep on doing it while shipping a game. And this is what we're going to be talking about.
So what we need is to update the backend for upcoming graphic APIs while developing new features for new games. And all this has to be done by keeping up with the regular title release cadence set by Ubisoft. Well, since Far Cry 3, the engine has been designed around D3D11, means dynamic state set from the code and combined just before the draw calls. Less work for the developers, but more on the driver side. And art has free reign of whatever they want to do, so they can apply shaders to all kinds of meshes, and this is an issue. For the front end, there was also plans to upgrade the system for terrain, water, GI, and sky for upcoming titles, including an upgrade to lighting system towards a physical-based one.
And this is where we come up with developing a long-term technical vision and planning for this. I will break down the D3D12 challenges into three big aspects. There's resource states and barriers, there's render state management, memory management, and all of those three challenges would happily be like their own talk for an hour, but we only have 50 minutes, so we will be focusing mostly on one thing, which is the shader state side, meaning render state management for PSOs. So before we go into the details of this, a quick refresher. What is a PSO? It's probably easier to say what a PSO is not. A PSO is not the resource bindings, viewports, scissors, blend factors, reference values, and topology. Anything else is part of the PSO. So you have your shader bytecode, you have your stage descriptors, you have all the kinds of flags you need to set. All of that is part of your PSO. So why do we talk about this today? It's been nearly 10 years since the D3D12 announcement in 2014. So you would have expected us as an industry to help solve these problems by now, but it's clearly not the case. Just a quick overview of the games being released recently. We can see a lot of issues with shader compilation stutters during traversal of the game, long compilation times, and even Vulkan has an extension now where you can use Vulkan without using pipelines. That's not really, if somebody would have asked me what are going to be the challenges in 10 years from now, in 2014, I wouldn't have guessed that this is what our games would be looking like. So I think it's a worthwhile topic to discuss how we addressed it on Far Cry, and maybe have a studio ideas on how you can solve it as well in your project. So before we can go into the details on how we solved the problems, we first have to look at how did we actually offer our shaders.
And now we will have a look on how shaders are organized in Dunia. At the high level, shaders are defined by the concept of shader families. So what is a family? It is basically a group of shaders that implement a similar material responses. And we can have a family for skins, for car paints, for vegetations, for weapons, and much more. Each individual shader and their variation within a family has a unique identifier named the shader ID. It is basically an unassigned integer of 32 bits obtained by hashing and bitwise operation of masks. We have masks for shader families, shader options, shader variations, and all those masks are generated by the shader compiler. Well, the upside is we will always have a unique ID for shader and its giving variation. However, if, for example, we introduce a new family, we need to recompile everything.
So what is our goal? Like we set out, we want to set long-term vision, and that's what we did. We say, okay, we have a shader ID concept in our engine, and we want to map this, each shader ID to a PSO. Why did we want to do it? One, D3D12 is kind of like the expectation that this can be done, and we think it would be worthwhile to do, because the amount of state of like runtime overhead we have managing all that render state is not negligible, and we want to reduce that. We also want to reduce the possibilities for mistakes, because we've all made these mistakes where we set a render state for one draw call and then we forget to unset it, so the next draw call doesn't work anymore because now the blend state is wrong. So these things can get out of sync. So with a PSO, every state being coupled into a PSO, we want to reduce that chance of state leaking from one draw call to another. So these are really the two goals that we set out to solve. D3D12 requiring this was the motivation to get started on it, but not really the way why we want to do it. So bottom one is like, how would we envision it? Pretty much we just want to call draw on the command list, we give it a shader ID and all the binding information, and the rest should just work. No having to manage state, no having to set state, reset state. So all this should just work. But obviously, as you can imagine, there's lots of challenge ahead of us. So what is it? What is the state so that we start off with? We have shaders, which are offered in HLSL, and we have pipeline state, which is managed in C++ code. These two are fully separate, and we need to bring them together into one place. There's also no art restrictions. Every model could be used with any shader, and it was kind of expected to work. So that means, as an engine, we couldn't really assume that an object wouldn't change, because every object in the world could totally switch to a different unrelated shader at any point in the game. It could have been a weapon that turned into a normal object, or it could be a car that turns into a weapon. It was up to the art team to decide what they wanted to do. There were no restrictions. So that made it very hard, very difficult for us to get an idea what shaders are actually going to be used. What is our plan here? So we want to extend our shader compiler to allow the state parsing. This means we want to move the PSO states into each shader family. Since we are using something based on the good old FX framework and our shaders are offered in HLSL, we thought, let's just put a technique block at the bottom, add the render state we want to set, and extend this to support all the D3D12 state. This way we will have our shaders in HLSL, all the render state in HLSL, and we will have a parsing step that will take that information, put it into a data structure that we can later use for the PSOs, and then compile the PSOs with the correct state.
So how do we work with the art team? Previously, it was mentioned that shaders can just be applied to all kinds of meshes. Therefore, some clear rule for that has to be set. Shaders should define supported vertex format, and only model with matching layout can be used with that shader. Remember the notion of shader families? So now on, only shaders within a family can be switched on the same model. If a rule is broken, shaders will be replaced by placeholder materials in dev build. Essentially, the asset will show pink, as you can see in this screenshot below. Those clear restrictions early on give the art team enough time to adjust. The takeaway here is art pipeline in AAA development is long, and it needs as much time as possible to adjust. So start adjusting the workflow early on. Well, we now have a plan for Far Cry 5 to get us closer to solve our PSO challenges. But what about barrier systems? This is also very important for the then upcoming APIs. Well, even though it's a topic for another talk, we can certainly still give you a small overview in this one. Speaking of barrier system, this was a crucial task to get the new API working. The implementation is hashmap based, where resource stages and resource usage are tracked. The system uses an explicit binding model. Each time a user requires a new binding for texture, render target or buffer, annotate the resource with flags indicating its stage and usage. Resource and sub-resource dependencies are resolved just before draw and dispatches. The tracking system was first shipped on D3D11 Xbox console, where proper cache flushes and syncs are issued. But it can easily be modified to support newer API barriers at the time. Since Dunia rendering is single-threaded in many parts, this makes the system lightweight and easy to debug. However, manual annotation is time-consuming and might be error-prone because of the design decision, and the hashmap implementation might make the execution cache-bound. A lot of technical milestones were accomplished when Far Cry 5 released. Here are 3 major milestones among many ones. We now have a D3D12 compatible barrier system in place and used by Xbox One, although we shipped in D3D11. This will issue cache flush and GPU syncs. The system itself is of course not yet used on PC, but we do have a resource state validation system put in place in dev build. Secondly, the data restrictions mentioned earlier during the presentation is now being respected by the art team. Moreover, the shader system is also being prepared for the introduction of PSO. We have a data builder and loading system completed. We also did a first pass of modifying shader files by adding render states in it. Now I will give the mic to Jendrik, who's going to talk about the challenges on Far Cry 6.
So, Far Cry 5 comes to an end, and we have to start thinking about Far Cry 6. New production, new challenges, and also a new studio. So what challenges are ahead? First of all, Far Cry used to historically mostly be a Ubisoft Montreal-led project. But with Far Cry 6, this responsibility changed, and Ubisoft Toronto got the opportunity to be the lead studio for one of our games in the franchise. So what are we like? That is a challenge. New team, new leadership. Montreal, we are still here, and we have still lots of expertise in Montreal, and we work really, really closely together with Toronto to solve the challenges. But there's also lots of challenges ahead. Like, what must-haves do we have? We have to support DFD 12 for PC. We have to support Vulkan for Stadia. We also have to support PS5, and Xbox Series X came out, which means we can no longer use DFD 11 on our console targets. So those are all must-haves. That's a huge amount of must-haves. But we have a couple of things available. We have DFD 11 on PC and Xbox, and we have a PS4 implementation. So you can see there's lots and lots of work ahead. We have a plan. We started down this journey to solve the problems, but it's still a lot of work. So how do we even try to tackle this challenge? So we came up, obviously, with a high-level plan. We want to start working on a PC platform. We were going to do either Vulkan or DFD 12 to start working on it. It was pretty much arbitrary. We could take one or the other. But our PC and Stadia team decided we were going to start going down the road of Vulkan, because they're going to be responsible for doing Stadia, and our first external technical milestone was Vulkan. So that was a good enough reason to get started on Vulkan. The new targets, like, why did we start on PC? The new targets like PlayStation 5 and Series X and Stadia had to follow a little bit later on. Why is that? It's pretty much just because it's new platforms, so we had to get the engine running. You have to set up the build steps, you have to get it actually compiling and running and get file loading working, packaging, all the realities of actually starting a game on a new platform. And we can't really get started on doing graphics for these platforms before the actual game can boot up. So that's why we started on PC. And once we had the engines running up on all these platforms, we would start bringing in new targets as well. Then there's obviously new platforms, so lots of general porting work. But there were some things that we already solved, like we have a barrier system for Far Cry 5. And we have our data annotated, so it's a huge time saver for Far Cry 6. We didn't have to implement a temporary solution for barriers. We could just use the system we already have. It was obviously not perfect. It was used on a system where the only validation system was our own. So Vulkan on DFD 12 validation layers often disagreed with the rules that we had in our system. But it was already there, and it worked really quite well. There was some mistakes had to be fixed, but it was helping quite a lot. And a huge time saver as well. All our systems are written for it. Programmers are aware of it, so all new systems are already having barrier information in there. So, and then very last step is really general reporting process. Once you have a version that actually works and runs, it's time to take advantage of what you can do now. So how do we get to all these new APIs and platforms? Like, we have 3 new APIs, and the way Far Cry was offered, we typically had a separate code implementation for each platform. That worked okay if we had 3, because we had DFD 11 on PC, DFD 11 on Xbox, and a PS4 implementation. So that was 3 files. But now we would also add Vulkan for Stadia, so that would be number 4. We have DFD 12 for Xbox, number 5, and we have DFD 12 for PC, number 6. And we would also add a number of PS5, so that's number 7. So that doesn't really scale. And then we have 3 new platforms, so how do we approach it? At the time, a new shared Ubisoft initiative came up. It's called Fusion, that we took advantage of and worked very heavily with our colleagues on the other game productions. It's a low-level API that is abstracting the common APIs. So instead of us writing code that directly interacts with the API, we would talk to this abstraction layer that is shared. So our porting process was really porting from our custom system to Fusion that would internally call the APIs that are specific for the platform. This way we only had to port once to the new API and have a single target. All our code always talks to the same high-level target, as you can see in the description. We have a shared small layer that implements whatever we need to do for abstractions for our engine, and our games on top rely on that abstraction, and then we call it into Fusion hardware abstraction layer. That is really doing the heavy lifting of calling these specific APIs. What does this enable? It enables us to write one code path. We have to debug one code path. And then we can share a lot of the code path work that needs to be done behind the layer. We can share that between different engines game within Ubisoft. And that's what we did. It was a great time saver, and it was a great approach that worked really, really quite well. It was a challenge to get into the mindset at first with some team members, but we solved the challenges and solved the problem. And I think it was quite a success. So let's get into the PSO magic. So what did we do? We have stated sets everywhere in the runtime side of things. And we have shaders that contain no state. We will start with, I think what everybody starts off with, it's on-demand PSO compilation. So what do I mean with that? That means every time we do a render state, we cache it into a structure. Every time we do that. And then each draw call, we will go into the state that we have in the cache. We will hash it. We look up in a dictionary, do we have a PSO that matches it? If we have a match, we get the PSO, we set it, and we render it. So that's pretty much the obvious thing. But one thing we probably do differently than most other engines is we never stall if we can't find a PSO. If we don't find a PSO in our lookup, we will skip the draw call until it is ready at some later point in the frame. But there might be certain objects missing for a couple of frames.
Here's the philosophy of this engine. If dispatch or draw shaders are not ready, do not stall, just skip the call. For example, our dispatch function will return a boolean indicating whether the dispatch was successful or not. And on the high level, the system can decide what to do next. If you look at our shadow system, for example, in the pseudocode below, when a dispatch fails, simply skip the rest of the dispatch in the chain. Similar idea applies for draw too. We can monitor the availability of the shader. Now, on a side note, UE5 now support a similar way of doing this, since version 5.2. Well, this whole concept of skipping draw call is also very helpful when porting to new APIs. We have our own validation system with a list of known errors which are safe. So, if a draw call triggers such error, we can just skip it instead of potentially hanging the GPU. This allows us to get the game up and running faster and go back to fix individual errors on a case-by-case basis.
And we really focused on making iterative improvements. Like you can see, we did on-demand PSO compilation first. We then hooked up a validation system to keep the game running, and we can keep on working on it. This means like even if there's still lots and lots of errors and lots of non-optimal paths, we already have the game running. This means the QA can test, and we can keep on developing and improving the system from here on in parallel. While the QA is already working on a game that works, people can test it, and new issues that will happen with new systems being developed can be detected quite quickly. And that was really, really important for us, and really something we really focused on. And I really want to stress it's really, really important to keep making iterative improvements. So how do we improve our shader system for now? So we had a goal. We have shader IDs and we have on-demand PSO compilations. So why does shader stuttering typically happens? Or in our case, why do objects would be missing from the world? And it only has to happen if a PSO is not ready. So how can we make it less likely that PSOs are not ready? What do we have in the PSOs or in our shader families? They all have a really long list of variations. And all these variations are treated as if they're the same importance. So we can see like there's vertex formats, output formats, can an object burn, is it wet, is it being influenced by the wind, is it skinned? But are they really all of the importance? I don't think so. Like if you look at this list, for example, we've marked a couple of them in green. You look at these burning, wetness, wind influence. Are these really the same importance as if an object is skinned or if the vertex format has normals or tangents? I don't think they're the same importance. So let's split these up. So we end up with two sets. We have essential variations and we have optional variations. Like what is essential? Essential is pretty much everything that if it's wrong, you will get possibly severe artifacts. If you read the wrong vertex format, your object won't be looking correct. If it's not skinned, in the best case, it will just be in the T-pose and just stand there as a T-pose character. If it's and if it's missing output formats, it probably just goes all over the place. So those are really essential. You have to get them right. But there's optional concepts as well. Like an object is burning, it can be wet, or it could be influenced by the wind. So if we look at the burning example, for example, we can see like you set it on fire and the object will slowly start burning. That means it will slowly start being black. So would we mind if that transition happens a couple of frames later? I don't think we would. Like it happens slowly anyway, so missing a couple of frames won't be an issue. It's way better than not seeing the object for 2 frames. Or in other cases, when you are stalling, having a frame stutter. So I would say this was really a good breakoff. This makes it possible that objects are optionally marked, optional effects are missing for a couple of frames. Obviously, there are cases where there might be undesirable effects, where a camera expects you to do things, like you're very close to an object and you want to swap it immediately for some kind of a technical effect, artistic effect. So obviously, we will see those, and those happen, and QA will flag these. We get Jira, and we'll fix them. There's ways of doing them, preloading shaders, things like these. But it's a great starting point. So what can we do then with this specific win? It's kind of what I mentioned. We can fall back to less specific PSO. So we can start looking for fallback options if one of them is really not ready yet. So how does this work? We pretty much take the variation that the object is requesting. We could be an object that's burning. And then we can be like, okay, we look in our dictionary, we don't find the PSO. So remove the optional flags one at a time. Remove the burning flag. Is it there? If you have one object that is the same shader but not burned, we will just use that instead. It's there, we can use it. And we obviously start compiling the PSO in the background, so at some future frames it will be ready. And if we don't find it, we just keep on searching. And if we really have to go back all the way, we keep on going, and there's just no shaders, we are back to skipping draw calls. So at this time, really, the game is running decently. It's quite, it's testable, it worked quite well, but we really want to do better. And this is really where, our vision comes in. It's a long project, but also this task will be really, really long, and we want to get closer to it. So we'll just start working on it as much as we can. We decided to start our transition on Xbox Series X. Why did we do that on Series X? It's just the reality of AAA production. We in Montreal owned the Xbox platform. We had scheduled time for this project in our schedule set aside so we can solve it, and we thought it was really important to solve this problem. But there's also, we are worried less about regressions happening in those platforms because it was our least tested platforms. It was still tested, but all play tests and things like that didn't happen on Series X. So we were less worried about causing regressions that would cause us losing valuable player information. So how do we get actually starting it? At the start, you have pretty much 2 sets of different states. You have the runtime shader, and that's the one we know is good because that's how the game is run up to this point. But we also have the state in the shader. In the best case, those 2 are going to mesh exactly. But that's not always guaranteed. So how do we really need to do this to solve that these need to be the same? We've set up the shader state during Far Cry 5, but we all know things that are not used are typically not correct. So what we do need is a validation system that catches these kind of mismatches.
A new validation mechanism has been put in place to be called by the draw function to verify states. It is designed with 5 modes, and each one is an increment of the previous one. First, the system can check for the shader state against runtime ones, and if a mismatch is found, prefer to use the runtime state. And secondly, we can enable warning and log them for debugging purposes. Thirdly, the state specified by the shader is preferred over the runtime state, and we can log mismatches. Then, there's also the possibility to skip draw and log warnings. In the end, the ideal case to only use states preset by the shaders. But to get to only use data state, we need to get there gradually. And although we made tremendous effort to update our shaders with the proper states and having our team respect the constraint we set at the beginning of the project, there was still 90% of the case falling back to runtime state when the shader pipeline was first turned on. So what was the common issue? Most mismatches come from the render target format or blended mode setting. It sounds bad that we have 90% failure rate, but most states are just a common state shared in files included by most shaders. For example, in the code below, blended state fx file contains a big portion of the shared state. Then we started to get those low-hanging fruits. Fixes continued from the 3D side until the game can boot without breaking on warning for a couple of minutes. Once we were confident that a big portion of the state mismatch issue were fixed, we deployed an on-screen warning feature to our local QA tester. The warning contains information such as shader name, variation, provided state versus expected state. The 3D team QA started to use this warning to relay the newly found issues so programmers can continue to fix them. Then we expanded the warning system for all QA members to use once there are no more regular warnings remaining. If a warning shows up again, QA can just use this information to log a Jira like any other bugs. Near the end of the closing for Far Cry 6, most of the state issues are solved via code changes. However, there are still some cases where our team's involvement is required. We would like to expand our previous on-screen warning system further. The goal is to give technical directors enough information to track down the causes and assign the issue to the right person on the art side without programmers' involvement. This finally led us to use an in-house API to generate Jira directly at runtime to not further divert QA resources away from area requiring more testing as we approach the final deadline to ship the game. We validate the geometry layout and additional information against what the shader expects. Other information validated include name, indices, stream, type format, for example byte or float, offsets, the data classification, in other words, if it is a vertex data or not, render instance step rates. The diagram below shows a summary of the elements that are compared during validation. One Jira for each geometry and shader combination is automatically created when a mismatch is detected. This gets automatically assigned to directors so they can redistribute the task to the proper stakeholder. Now, let's have a look at the testing and validations in more detail. Starting with the test coverage, the work in Far Cry 6 is rich in detail. Therefore, there are many environment settings to test. Each of them contains different type of asset, which means different families of shader state. For example, in the city, we have a higher chance of encountering vehicles, which provide coverage for vehicle families of shader. Same idea for the dense forest and ocean, which provides coverage for vegetation shaders and water system coverage, respectively. Moreover, there are also the possibility to change weather settings. This can trigger different response such as wetness effect, lightning, rain particles, and much more. All this combined with different gameplay settings such as navigating the game menu, driving vehicles, mission gameplay in general, creates a large permutation of test cases with many assets loaded on screen, hence many shaders tested. Testing is done with a combination of manual testing by our QA team and automatic testing by bots and scripts. For completeness, the map is divided into well-defined sectors. The first part of the automatic testing is deterministic. We spawn at fixed locations across all sectors and set weather and time with known settings. A script can then collect screenshot and profiler captures. By doing so consistently across different builds allows us to spot performance and memory regression. The second part is done by using a bot feature from our AI and game dev team. A player bot can spawn randomly in any sectors and start to play the game on its own. The bot will shoot guns at enemy, steal vehicles, and drive them, for example. This sort of testing triggers additional effects, otherwise unavailable by simply spawning into the game. In the end, it greatly helped us to detect any rare shader bugs, which QA team might not have found. Of course, we do still have a QA team which is crucial for testing features like game menu, item inventory, cutscenes, story flow, gameplay mechanics, and any other element that automatic test cannot cover. By using the iterative method combining QA pass and auto test pass to shader state mismatch detection and to fix and validations, we managed to ship our shader pipeline system in a very stable and polished state.
And
now I'm going to hand the mic back to Jendrik, who's going to talk to you about some edge case and fine-tuning the experience overall.
But there's also a couple of interesting edge cases that we found out at the end of production. So, for example, one would be like if you aim at an enemy, we would always get an assert with a mismatch. But what's going on? Why is it? We couldn't see any difference, and that was actually the main problem. There was no issue. We couldn't see a difference, and that was the issue. There should have been an outline on every object if you aim at it. It should be marked, but it was just missing. So what was this all about? Why did this not work? And how did we not catch it before? It's because the system is implemented using a different system. Like we validated shader overrides, but the outline used a different code path. And it just expected that would bypass all this. And it needed to apply an outline to pretty much any object in the world, and it used just a different system, so we didn't see it. And the challenge with this is we need it for every single object, and all different have different model formats and vertex formats especially. So what do? We're just going to add a variation for each vertex format. That could be a lot if there's a lot of complexity in your shader, but there are different ways. So one thing that we assumed to do, we actually ended up doing, is to rely on the custom vertex fetch. It's something we haven't used on Far Cry. Lots of other engines do, but Far Cry hasn't used it. So the idea is pretty much to decouple the vertex format from the model from the vertex format expected by the shader. So instead of using the hardware pipeline to assemble these things into a complete view of the vertex on a vertex before the vertex shader runs, we will do that custom in the shader itself. So this is called programmable vertex pooling. If you look for it, you will find some OpenGL books discussing this in a lot more detail. So for this outline shader, we only know two things. We only need to know two things. We need to know the position and the normal. Why do we need the normal? Because we expand the objects to form an outline. So we don't really care if there's two sets of normals, if there's a tangent space, and we don't really care. We just need to know normal and position. So how do we solve that? Pretty much each model on the C++ side exposes a structured buffer view onto the data streams it has. And then the C++ logic can query this and bind these to the outline shaders. What happens if the object for some reason doesn't have it? It will just bind a dummy string with dfd12 defining on how you do this in the boundary cases on edge out of bounds. This worked really well. It worked really, really well. The system was designed to reduce shader variation, but it's very flexible, so it's a great side effect from doing this to solve the shader variation problem. So we created a very flexible architecture that we would have used probably a lot more on future projects. We really did it at the end. Each shader ID in our engine maps to a PSO. It was a huge amount of work, but we were really grateful that we broke this down into steps over multiple games. Now our runtime code can be super simple. Like most cases never really need to deal with render state at all. It's all centrally managed in common header files where we can change them. The shaders own the whole state in a single place as well, so if we need something, or look something up, we know where to look. We don't have to search the C++ to see where that state gets set. We can look in the shader. No more state leaking because of it. It's all controlled. And I think it's really worth the effort, and it makes for a better engine architecture if you designed for it. And I think it really shows it can be done on AAA games that were never designed to solve this from the day. It's doable. It takes a huge amount of work and dedication, but we showed it's doable. But this is obviously not everything, so we can do more. So what do we have? The runtime is there, but the very first problem of most games is the very first time you play the game is when the shader cache is not ready and you won't have the information that you need. So we have a couple of techniques here to solve the problems. One is we collect the runtime PSU usage. This happens, and then we compile shaders on the very first load. So how do we collect the PSO usage? There's a huge amount of variations, shader variation that we can use in Far Cry, and most of them are not used. So what do? Every single playtest session and QA test session as well is talking to a database. It tracks what kind of shaders we use, and it consolidates all of the sets in a single place. So we have a single list of PSO, and then we can sort it by what is most used. We use this list to get roughly the most 10K most used PSOs, with some manual control about like we have to load some copy shaders and clear shaders, things that get used like once are super important. Things that will render the main menu, for example, are important because you want to have the menu working while you're waiting for the shaders to do. And all these shaders are compiled on boot of the game. And by the time the menu loads, we are sure that these shaders work. And we can run the game safely with a good preloaded set of PSOs. With the things we added with falling back to less specific PSO, this makes for a great base list. But we have another step that really was introduced in Far Cry 5. It's the priming during the loading screens. So if you took away our loading screens in Far Cry 5 and Far Cry 6 for the matter, you would actually see at the end of the loading screen, the loading would finish from disk, but the loading screen wouldn't go away. What actually happens is once we're done loading everything, we spawn the player into the world, we pause the world around it, and we start rendering. We will spin the character around its axis, looking in all directions all around him. And this spinning and rendering happens while the loading screen is up. Why do we do this? There's two reasons for this. One is we need to prime our virtual textures on the terrain. While we're spinning, we will track how many virtual texture pages are not initialized yet. And if there's any, we don't remove the loading screen. And we extended this to also load the shaders. So if we have any shaders that are not ready, we will not remove the loading screen. This way, we can be certain that when the loading screen goes away, we don't see low resolution textures from the virtual textures, and we don't have shaders that are missing. So at least at each teleport, we can be sure we will be done with a new location before we even get to it. So the player will never see us having uninitialized. And with this, we are already coming to the end of our presentation. We are now going to take a couple of minutes to look back at what we just covered. During the last 45 minutes or so, we've been discussing in detail the requirements and solutions that we developed for the Dunia graphics pipeline. But there's more to it than just shader solutions. I think there's 5 main technical lessons learned that can be applied to a wide variety of problems in game development and software in general. First of all, when there is a major technology change upcoming, really take the time to identify and tackle the architectural changes required first. Look at how can we make our product better with new requirements. And then really start setting up the supporting systems earlier. Most problems can have systems that need to support them, and those can take a long time to implement. Start on that early. And then really take the opportunity to see new restrictions as an opportunity to look back, to look for better design solutions. Not just look at the annoyances that you need to solve. And really use an iterative design process. Each step should get you closer to a shippable solution and a solution that you're happy with. And really think long term. Do not limit yourself to the current project timeframe. Always think longer. This puts you into the right mindset to solve problems in the best possible way. And then break it down into the time frame of your project. What can you do in this project that will give you the best solution? And if you combine this with an iterative design process, you will always have a shippable solution. It doesn't matter when the game comes out, you will always have a roadmap ahead of you of steps to do. Games get delayed, and you will already know what you can improve. And that's pretty much the end of our talk. I really want to acknowledge all the many people who have worked. I had the pleasure of working with during Far Cry productions, from Far Cry Primal to Far Cry 6. There were so many people who made the Far Cry games possible, not just on the rendering side, but especially the rendering side, the engine, the artists. It was a great experience. I really acknowledge that the work done, presented here, is really a product of a team. And none of this could have been done with the amazing team. So thanks for everybody who worked on these projects.
Likewise, I will give a huge thanks to everyone who was on Far Cry 6 and to everyone who made the previous Far Cry game possible. It was a fantastic team and a fantastic learning experience. Thank you again. Now to our viewers, a big thank you for your time and for listening to our stories today. Now we are open to answer your questions.
Thanks so much, Jendrik and Kong. Very much appreciate the presentation. I'm going to go to our questions now, which the team has been putting together. Grigory Javadian asks, when doing resource state tracking, did you have to defer actual command buffer recording so that the resource transitions could be inserted at the appropriate time?
No, we did not. The engine's a bit like a fork join. So we have multi-threading within paths, but not across them. So the states are ready when the paths arrives.
Great, thank you.
Thank you.
Sebastian Altonen asks, did you investigate using dynamic branching, an Uber shader approach, before the optimized variant of the shader PSO was compiled? For instance, falling back to a slower version instead of skipping the draw?
Like, we did not in the overall. Like, one of the aspects that's specific for us, like all our shaders are handwritten. So we would have need to go in and change all of them to actually support dynamic branching. So in this case, we didn't. And maybe was probably asked earlier in the talk, and it becomes a bit more clear afterwards that we had other ways of dealing with the problem that made it less of a problem for us. So we didn't have to investigate that solution.
Alexander Joubert asks, how did you manage PSO permutation explosion with all the states shader permutations on a similar shader system in a different engine? We hit this issue. It was easy to have hundreds of thousands of PSOs. We had to go through the permutations manually to remove the ones that were not really used in the game. I'll add, I think on Call of Duty Advanced Warfare, we peaked at around 450,000 unique loaded shaders. Like for a level. I don't know what we didn't have PSOs back then, but I'm very sensitive to this problem as well.
Yeah, that's probably like most of us. We probably also ended up with some of that number. I don't know off the top of my head anymore what number we had. Yeah. But yeah, it's definitely a thing we've been looking into. Like, we've always been trying to remove them. When we had the opportunity, we would remove them. We didn't do, like, it was definitely more with the PSOs, so it was more of a task to actually remove them. But it was because of the way we preload only the ones we actually use. It wasn't too much of an issue in the end. Like, we would just have that way of falling back to the ones that we actually use. So it never was much of an issue. It was more of an issue on the build side of things because you had to actually go in and compile and parse all of that. So that was an issue. But yeah, it was just like, we would reduce it when we have the chance, but it was never like a major problem.
Yeah, it's interesting reflecting on Call of Duty. I mean, we I think are maybe one of the few teams that does exhaustive like pre-compilation of every single PSO, but kind of harking back to Sebastian's earlier question, we also spent a significant amount of time on scalarization techniques to allow us to do efficient versions of, quote unquote Uber shaders on console to try and reduce and manage our PSO count. So both of these questions are close to my heart. Omid Mirasmaili, apologies if I mangled that, asks, since you already decided on Vulkan for Stadia, why not just go for Vulkan on PC as well instead of DX12? And this spawned a long API discussion in Discord as well.
Well, it was less of an API discussion. It was pretty much a business decision. Like, I think Far Cry 6 was a business deal with NVIDIA to add. So we had to do ray tracing as well. So we had to do ray tracing. And I think at the time there was no ray tracing on Vulkan. So that was the decision.
Yeah. The NVIDIA and AMD GPUs, we had to add the ray tracing. That was the issue. So we have to support vendors on both sides.
Jussi Knutila asks, did you observe any GPU performance impact, positive or negative, after switching to programmable vertex pool?
I think we only have like one specific effect for that, and we don't have many character for outline on screen, so I guess the use case is very limited. I don't think we have any big performance issues here.
Understood. Nassim Damani asks, why not use the latest bound pipeline instead of skipping the draw call? On a homogeneous scene, it can yield some okay result. That sounds exciting. Go on.
But what would be an option? Like the latest bound one, like whatever happens to be bound?
Yeah, that's the spicy decision, in my opinion.
I guess it's an option to try, but I think we're probably going to run into issues mostly with corruption when things are not actually using the exact same vertex layout. And then you just get triangles everywhere and very undeterministic results. So probably not something I would try, but it could be a fun experiment.
Yeah, if you were worried about not getting enough JIRAs from your automated system, this would possibly take care of it. We do a variant of this ourselves in some of our graphic analysis tools, like when we're mucking around with the frame, but that's all for like offline debug stuff. Benoit Miller asks, since you gather use PSOs from internal play sessions, and you already script draw calls that don't have a PSO, how do you track missing PSOs on the live game? Is the missing stuff simply silently skipped?
I think we just don't skip it. We don't track any information like on this level from a live game. We ship a offline version of which PSOs to load when the game installs. You have that version of what it's going to load. So if anything gets added later on, in like, for example, for like patch, we would need to patch that file as well. If new shaders get added that are important to be preloaded. Most of the time, not the biggest problem for us, at least in practice, it wasn't too much of a problem. It was mostly be an issue when we change any of the global shaders and they have a new ID, and then we need to make sure that we patch them in. But for individual object, it tends to not be an issue because if we go to a new world that didn't exist in the previous original version of the game, it would probably be a loading screen. So we would take care of that during that process. But it's definitely something to look out for. Like you need to patch that file as well.
Yeah. Matt Patinio asks, for the PC build of the game, did you also have to account for different shader PSO variations based on user graphics settings?
We should, yes, we should, but we don't at this point. But yeah, you would definitely get different ones. So we had a couple of issues. So one of them would be like most of our testers would be happening on like latest graphics card. So they tend to have the ray tracing enabled. So if you try to preload all those shaders on something that doesn't have ray tracing, it wouldn't work. So we need to filter on that level also. We mostly filter on feature levels. So things that are optional for hardware, we feature out, but anything else we didn't in this point. So it might be a good thing to investigate for the next version of this.
That reminds me of a related question, which is, did you hard stop on players outside of MinSpec for the title? And did you possibly have issues for players like going really far down the MinSpec chain as well?
I must say, I'm not actually sure. I don't know if you know. I think we had a check that would check the driver version and things like that. So we definitely hit that. But I don't know if we returned, if we let them play with if they didn't met the requirements.
I think that's the PC team in Kiev that knows, and so we can come back to this.
Yeah. Tianning asks, it sounded like you worked really closely with your QA team. Can you describe what that collaboration loop was like? Was it mostly online meetings, async communications such as Slack or emails, or in person?
Now we have our some like there's the big QA team, and we have some QA tester embedded in our team. So we first work in close collaboration with those people first, and then once the build, like from what our system perspective is stable enough, then we can enable broader loggings and validation system for them to actual trial. Yeah, and yeah, it's mostly done in online meeting. And we have syncs between QA leads of our team and the actual QA team that tested the game.
Yeah, I think this is one of the most interesting parts. Actually, we talk about this whole conference as trying to talk about a piece of rendering programming that we don't really discuss at SIGGRAPH per se or other conferences. And I feel like this is also one of like the really interesting hidden sort of techniques of how we do professional development, is understanding how to leverage the rest of the team to achieve really interesting things around API transitions and stuff like that. So I really appreciate you guys speaking to that.
It was definitely also a challenge, like especially if you look at the timeline. We started in person and then COVID happened, so a lot of more remote. But Ubisoft is generally remote anyway for lots of places because just of the different locations where people work.
Yeah, massively distributed development for your teams.
Absolutely. Yeah. Different time zones, different locations.
Jacob Lang, I think your question was answered by Matt Patinio, so I'm going to skip that one for now, but let us know in chat if there was a nuance that was missed there. Robin Dussy asks, thanks very much for the talk. Were there any pitfalls in the deferred pipeline creation and draw command skips? It's fairly broad and more detail there.
I can just do a little bit of talking about it and maybe it will answer the specifics. So it definitely was like a challenge, but it's been something that we quite extensively test as well internally. Like it's quite common for shaders to be skipped if they're not ready in the way we do like our shader reloading. So if a shader gets reloaded, we would mark the old versions as not valid. So it's quite common to test shaders not being ready. So especially for 3D programmers who iterate on shaders, that would be a quite common thing to test. Yeah, the most common pitfalls we really passes that depend on each other. Like the second pass is not valid without the results from the first. Like draw indirect is probably the worst because you will probably get a GPU hang if you didn't initialize it at all. And you try to kick off like too much work for your GPU to handle. That was probably the most common one, but otherwise there would also be like issues with, like if something is not initialized at all, then you have nans that stick around for a while. So it's definitely, it was not a trivial amount of work to get that working, but it's like if you have it in your general workflow, it's not too uncommon to encounter these cases. So get caught quite easily.
Thanks. Jasper Becker asks, it would seem returning a Boolean from dispatch for skipping is quite error prone. Did you investigate using the C++ type system or types to solve this problem, or was it not an issue for you at all?
I would say it was just not something that we needed. I'm not really sure what the type system would help you with for that case. I guess just to make sure that you check the Boolean case. But yeah.
Yeah, I mean, I definitely, Call of Duty has, I spoke about this at the first course, we have a allocation system for resources and the draw calls that requires a little bit of careful management for us to do appropriate, error checking and handling. And I can maybe imagine something like that, but hopefully your call sites are not so frequent that it's a complicated problem for you in that regard.
It was never like really an issue. Like you could forget it, but most of the cases also didn't need to handle the case. Like it's only dependent calls. So it wasn't never really too much of an issue, but I can see it being it could be helpful to maybe make you think about it when you write a dispatch, like remember this could fail. Like it could be interesting. Yeah.
Yeah.
So
Aro asks, you mentioned spinning the camera on level load to preload pipelines. Did you need to do a similar preloading before entering through chokes in levels like doorways, or was it fine as is? So this is a like an occlusion of states question.
Yeah, we don't do that mostly because of the way Far Cry works. Far Cry doesn't really have many choke points in its level design. It's all open world, and we just don't have any choke points. So generally, it works quite well because objects tend to come into view from far distance first. So that tends to deal with it, and then we can fall back, like we mentioned at the end, to what is not ready yet, and then as you get closer you get those shaders. So generally it's not been an issue. Yeah,
is your worst case like a save state or something similar that's like at an interior to exterior boundary transition? Do the materials swap heavily between interior and exterior materials?
Yeah, those could be like the hardest parts to deal with, but then you tend to have like the pixel shaders would be the issue mainly. Like the vertex shader would be ready because you have probably shadows that get calculated from the outside. So those objects are partially visible to the system, at least.
Yeah, the spin is mostly teleport and loading on in-game. And just one thing I wanted to mention regarding previously the question asked why we shipped the D3D12 on PC. It was a partnership with AMD actually. Yeah.
With AMD?
Yeah.
Okay.
Just precision.
Yeah, if you've got a program manager furiously texting you right now to get those correct. I think we're at the end of our questions then. I'm just going to take a quick look at Discord to see if there's anything else percolating in. But otherwise, I'd like to again thank our presenters, Hong and Jendrik Ilner, and please everyone give them a hand in Discord. And we're going to take a short break and we'll come back for the next talk of the day. Thanks, everyone.
Thank you.
Thank you.